Section 8. Section 8, we're going to introduce linear models. And so Section 8, linear model. Linear model is an equation that describes a relationship between two quantities that shows a constant rate of change. We will often use the equation y equals mx plus b. You may recognize y equals mx plus b from earlier in your academic career, maybe high school or something. Next thing we need to talk about is slope. We're going to let that be letter M. It's the letter M because the guy that created all of this was a French person, and he named it M because it's to climb. It's like mountainous. It's like the French word for mountain, or like to climb. And so that's what slope means. Slope means to climb. It's the rate of the climb. So rate of change, the rate of the climb, that's what the slope is. We can calculate the slope by finding the ratio, the difference of the y's divided by the difference of the x's. And we're going to show some examples in just a minute. The letter B stands for the base, and the base has to do with the starting point. So B is where you started. So for instance, if you started a business with $10,000, then your business is starting at $10,000. But if you started your business and you had to borrow, let's say you borrowed $100,000 to start your business, then you would start at negative 100,000. Okay, and then you'd have to find how many things you'd have to do to break even. That's when it would equal 0, and then so on. Okay, so we're going to get more into this in just a second. A fair market rental lake for Lafayette was $749 in 2013 and $661 in 2005. Find the unit rate of change for rent in Lafayette during this period. So, we want to find the unit rate of change. That's the slope. We want to find the slope. Okay, we talked about the slope, which was the difference of the y's over the difference of the x's. But what is a y and what is an x? Almost always money is going to be the y's. We think of this as the output value. So almost always money is the output. And almost always time is the input. If you go further in math, you'll find, well, time is an independent variable. Time will pass. It doesn't depend on anything. It doesn't depend on how much money you make. It doesn't depend on anything. Time will continue to pass. But the amount of money will change, right? That does change. So time is the independent variable, and money is the dependent variable. So y is going to be money, x is going to be time. And so we need to take the difference of the money over the difference of the time. And so that's what I've done here, and this will find me the slope, the climb, the rate of change is 11. Okay, so that is $11 per year. If the rain is falling at a rate of 2.64 inches per hour, how much rain would you expect 3.75 hours, or 3 hours and 45 minutes, right? So for here, we're given the slope. They're telling us the slope is 2.64 inches per hour. And they're asking, how much rain would you expect at 3.75 hours? Okay, so how can we calculate this? Well, we know how much is raining per hour. We know how much hours. So I argue that if you multiply these numbers, you will be able to find how many inches of rain. And I've shown this by, you can see that the time is going to cancel because we'll have hours over hours. So you have 9.9 inches of rain within those 3.75 hours. Okay, the Environmental Club has saved 250 pounds of cans and promises to collect 15 pounds of cans each week. They will use the profits from the sales of the cans to buy additional recycling bins. If we construct a linear model to predict the number of pounds of cans that the club will have at the end of a given week, what is the slope m for this model? So what do you think? What do you think the slope would be? They gave it to us in the story, but what do you think it is? Pause this video and see if you can find it. Okay, so I think it's 15 pounds per week. Now, what do you think the starting point is? What's the B? What's the y-intercept? Pause the video and see if you can find it. I think the y-intercept would be 250 pounds, right? They tell us that they saved 250 pounds and they promise to collect 15 pounds per week. Okay. Same question. Use a linear model for the collection program to predict how many cans they will have in 28 weeks. So see if you can pause this video and then calculate how many cans they'll have after 28 weeks. Okay, so I think it's going to be 15 pounds of cans per week times 28 weeks plus the original 250 pounds, and that would be 670 pounds. Now part D says, use a linear model for the collection program to predict how many weeks it would take to have 550 pounds. Well, I just found that it was, for 28 weeks, it was 670. So it's going to be less than that, right? It's going to be less than 28 weeks. Notice that we start with 250 pounds, or we're starting with that, right? But the way I'm going to do it is I'm going to set up an equation. I have 550 equals 15 times t stands for weeks, plus 250. I'm just going to use algebra to solve. I'm just going to use my algebra skills to solve. So first thing I'll do is I'll subtract the 250 on both sides. And that gives me 300 equals 15t. And then I'll divide both sides by 15. And I get 20 weeks. It would take 20 weeks for them to collect that. But they started with 250, right? So 20 weeks to collect the rest. The cost of an LCD TV dropped from $800 in 2012 to $700 in 2014. Find the unit rate at which the cost is decreasing. So that's suggesting to us that we need to find the slope. So let's find the slope. What would the slope be? We take the difference of the price over the difference of the time. I find that it's dropping $50 per year. Okay. Part 2, construct a linear model to predict the cost of an LCD TV and use it to predict the cost that it would be in 2021. Okay, so we know the slope. It's dropping $50 per year. It started at 800, or at least our story problem started at 800 in 2012. So I made myself a formula. Y equals negative $50 plus 800. I can plug in the difference in time, so it's 9 years from 2012 to 2021. And then I can multiply 50 times 9, 450, minus 800, $350. So that same TV would be worth $350, or at least by this model it would be. Okay. In this example, the cost of renting a kayak is represented by the equation y equals 8x plus 5. What does the slope of the equation represent? So that's the number 8. But what does the 8 represent? So pause this video and think about that for a second. What does the 8 represent? So I think the 8 represents the cost increase for each hour of the rental, right? As the amount of time goes, so does the price. It goes $8 per hour, right? So that's what the 8 represents. You're going to see some questions like that in your homework. So hopefully that kind of gets you started on thinking those types of questions. Next thing we're going to talk about is correlation, a relationship between variables. This is going to be kind of the beginning of our more abstract things. It's very easy to answer the questions if you answer them quite literally. The deeper you think about some of these future topics, the more puzzling it will seem. But I don't want to scare you, so let's just dive into it. So a correlation between two variables. A positive correlation means that it's following a positive trend. A negative correlation means it's following a negative trend. The strength or weakness of the correlation is determined by how clustered or widespread the data values are from a straight line. The closer all the dots are to the line, the stronger the correlation. So in this section of the class, we're going to start looking at data. This is not mathematical models like we were talking about before. This is real life empirical data. This is not just a function that mathematicians are creating. This is real life points, okay? So you can think of, obviously, COVID is something that we think about and hear about all the time now. And so you could look at the data of COVID transmissions, and you could look at the correlation between those transmissions and something else, maybe people in vicinity of each other, or something like this. So you could look at real data and see, is there a correlation between two ideas? So here's an example. It's just a completely general example. There's no story behind it. But each one of those dots there represents a actual point. And the black line there, it's kind of inside the points, that is the trend line. Okay, so the trend line is the mathematical model that is an approximation of what the dots are actually following. And so our correlation is, how well does that line represent those dots? Okay, well, you might not have any room for comparison here, but this is extremely close. I mean, real life following a mathematical model there, that's really, really close. If you look at that graph there, you might see that there's a thing called R squared value. And the R squared is 0.994. Okay. So I would say anything that's above, I kind of think, you shouldn't think about it this way, but this is the way I always think about it. If you think about them as like, that's their grade percentage. So this is like a 99%. Okay. It just gives you a frame of reference. So that R squared value is always going to be between 0 and 1. The closer it is to 1, the better it is. And so this is really close to 1, right? And so this is actually really, really, really good. So this is a positive linear correlation because it's going from left to right and it's going up. So there's a positive value there. What value does the model predict for the correlation of carbon dioxide in 2000? So this is the year 2000. So I guess this model is predicting CO2 emissions or something like that. And we're saying how much in the year 2000. So at the bottom there you can see we have some years, 1970, 75, 80, 85, and so on, up to the year 2010, and it kind of trails off. So what is the value for the year 2000? Well, if you look at that chart, you can see that there is an equation there. Y equals 1.6178x minus 286.4.6. Very hard to see, but it's there. You can plug in the x value and find out exactly what that would be. So if I plug in the year 2000, that's going to tell me exactly what the chart is trying to show me. So I find 371 parts per million. So we're not even really talking about CO2 right now. I'm just talking about how you can extract even more information out of these graphs. So once the information is graphed and they have a trend line, that means you can plug in the values and find for a specific year or a specific x. What value does the model predict for concentration of CO2 carbon dioxide in 2024? Well, we don't know. We don't know about 2024 because this thing only really goes up to 2010. But we could plug in 2024 and we could see what it predicts. So when I do that, I get 409.83 parts per million. But this is just some practice of getting used to trend lines and looking at data.